Now let's take up some discussions of actual enzyme mechanisms, some examples. We'll use the serine proteases as a sort of an archetype of enzyme mechanisms, and hopefully we've discussed serine proteases enough in class already that this won't seem terribly frightening or confusing. Let me just remind you that proteases cleave peptide bonds through the addition of the water across this sessile bond here, the sessile or breakable peptide bond, and we see that that results in the formation of a new carboxyl terminus and a new amino terminus, two new products. And here is the enzyme. I believe this is chymotrypsin we're looking at. One thing I'll note is that there's some sort of beautiful internal symmetry here, but what we see is that we have a little barrel here, a little barrel here, I like that, but we see this catalytic triad, aspartic acid, histidine, serine, forming our nucleophile here and highlighted in red. Okay, let's look a little more closely at this catalytic triad structure. And we call it a catalytic triad. Of course, it's a trio of amino acids, but we see them repeated very frequently in other serine protease structures. There are some variations on this theme, but in general, we see that the aspartic acid serves to position the histidine, right? This hydrogen bond that's formed with the histidine. Positions and immobilizes that histidine so that it can actually be a good base for abstraction of the protein of the proton from the serine hydroxyl. Now, the serine hydroxyl, of course, becomes the nucleophile, and it does so because that histidine can form a strong interaction with its proton, and so oftentimes we'll think of this as being abstracted, although it's probably more likely that there's a concerted interaction that takes place between the hydroxyl oxygen, its substrate, as we'll see in a moment, and the histidine itself. In any case, the histidine is a nice base, all the better because of the strong interaction that it has with this aspartic acid. All right. Here's our first look at a mechanism, and we see the active site is assembled here, and actually the proximity of all of the amino acids in the active site is enhanced by when the substrate is bound. So we see in step 1 here that the substrate binds. This nitrogen abstracts a proton. Electrons from that bond go to attack the carbonyl carbon here, and we see those electrons kicked out to the oxygen. And again, we see the same structure forming here. So the activated serine attacks the peptide bond. This is a nucleophilic attack, and we see that results in the formation of this oxyanion species here as those electrons are kicked out to the carbonyl oxygen. This is referred to as a tetrahedral intermediate, and it is an observable intermediate. What I want to say, though, is that we form an unstable structure, and that's our transition state. Again, that's the state that the enzyme serves to stabilize in order to accelerate this reaction. But I hasten to add, as your textbook does as well, that we want to be careful and distinguish between something that's an intermediate that we can physically observe through experimental means and a transition state, which is a sort of a hypothetical high energy state that is not something that's observable. So we often refer to these interchangeably, tetrahedral intermediate and transition state, but it's important to make that distinction. So in any case, what's formed in the first step of the reaction is this tetrahedral structure that then immediately collapses, and that's what these arrows are showing here. The electrons kick back down to the carboxyl, the electrons go back to oxygen's proton. We take the proton back from our base. Now this histidine has become an acid, giving back its proton. And then what happens? Well, let's see. Before we see what happens, let's remind ourselves what's happening in this with this oxyanion state. The oxyanion hole, so sort of a microenvironment that's conducive to the population of this oxyanion, is created through a hydrogen bonding network presented by the amino protons of the backbone of the enzyme. So we form an oxyanion hole by creating hydrogen bonding partners with this negatively charged species. So we stabilize the intermediate through a pocket lined with polar residues, in particular forming hydrogen bonds with the backbone itself. The stabilization of the intermediate can mean a rate of acceleration of up to 10 to the 12. Not in this particular case, but we'll come back to that. But the bottom line is that this stabilization of the transition state and of this intermediate it results in a dramatic rate acceleration. Okay, so here we show the regeneration of the active site. So in the previous example, in the previous step, we kick off one of the amino end of the protein here when we break this bond, right? When we retake our proton from the histidine, and now we see that what's required again is that this again becomes a base, abstracting a proton from water in this case, activating that water, activating it, and so that the hydroxyl can now attack the carbonyl carbon of this acyl enzyme. So here we see that this is an acyl enzyme. We've lost the amino group of the protein. We've done the cleavage, but we're still stuck with an acyl enzyme intermediate structure that must be cleaved from the serine hydroxyl in order to regenerate the active site. So in this case, water is behaving as the base, activated by the histidine, and again we form our tetrahedral intermediate, although instead of the amino end of the protein, now we just have a hydroxyl. And the collapse again of that oxyanion results in the cleavage of that carbonyl carbon serine hydroxyl oxygen bond, and we take our proton back from the histidine. Right now, the histidine again is acting as a base, as an acid instead of a base, and we release our carboxyl end of our protein, of our second part of the product, and we've regenerated the active site. So again, histidine acts as a base, activating water. Water can then attack this acyl enzyme intermediate. Formation of a similar tetrahedral intermediate as we form in the first reaction. The collapse of that intermediate happening and concomitantly with the abstraction of a proton from that active site histidine and the release of product. We've talked in class about subtlysin, which is a serine protease, and we've talked about the form of these data already. This is a bit of a review in that case. What we're looking at, of course, is the substrate concentration on the bottom, increasing substrate concentrations, and the reaction velocities measured for each of those. And we see that this looks like a nice Michaelis-Menten kind of kinetics, and we see here in open circles the wild type enzyme looking like a very good enzyme, reaching saturation above 1,000 micromolar substrate. And then we also see that when we mutate the active site away, remember, I'll show you again what those mutations are, but this fourfold mutant is effectively inactive. Now we say inactive. There's obviously some activity here, and we'll talk about that on the next slide. Again, this should be some review for us, but bottom line is that the wild type has this catalytic rate, 6 times 10 to the 1 per second, and we see that when we add a cysteines to aid in purification, that's what this S24C is. We don't really affect the rate very much. We wouldn't expect it to. We're not making a substitution in the active site. But now we see immediately when we mutate the serine 221 to alanine, this is what we believe to be our active site serine. We take a massive hit in the catalytic rate, right? This is a 6 orders of magnitude change in the rate constant of the reaction. So we basically already more or less destroyed the enzyme, but we can make it worse. And it's interesting to note that the histidine, right? So when we mutate the histidine instead of the serine, we still see a very large change. Not quite as bad as the loss of the active site nucleophile, but still quite bad, telling you that the histidine activation of the serine is critical. Likewise, when we mutate the aspartic acid, which I said orients and activates that histidine as a base, we see still a diminished effect, but still 1,000-fold difference between the aspartic acid mutation and the wild type. And then there's other combinations, but let's just focus on this one, DHS substitution. Again, 7 times 10 to the minus 5 versus 6 times 10 to the 1 in terms of the catalytic rate constant. Massive effect on the retardation of the enzyme's kinetics. We see that Km doesn't seem to be affected very much. There's some effects on Kcat over Km, but we won't focus on those for the purposes of this discussion. I refer back to our in-class discussions to review that. What I will point out to you is that in the absence of enzyme, we can measure a rate of hydrolysis of the substrate, and it is still 1,000-fold slower than the triple mutant. So what does that mean? Let's again look at another figure that describes this. We can destroy the active site, and what we see then is this massive 6 or 7 order of magnitude loss in the activity, regardless of whether we take away the serine or the histidine. This is really important to note that both of these are critical for the function of the enzyme. Aspartic acid less so, but still important. And when we remove them all, of course, we still have the same much drastically diminished impact. Now, what I was trying to draw your attention to before is this uncatalyzed rate constant. And in fact, what we see is that there must be something about the enzyme itself that isn't part of the active site itself that still supports hydrolysis of the peptide bond. So the hydrogen bonding network is not absolutely required for hydrolysis, and perhaps what we would invoke might be two things. First of all, that oxyanion hole is still supporting the formation of the transition state and its closely related oxyanion tetrahedral intermediate, and as well reminding you that there are plenty of binding site determinants that keep the substrate in place that might support stabilization of the transition state and therefore acceleration of the hydrolysis. In this case, perhaps the nucleophile would have to be a water molecule, but even in the absence of our catalytic triad, we do see some activity. Okay. These are some reiterations of old ideas for us, just reminding you of the idea of the conservation of this active site. Here are 3 structures overlaid: chymotrypsin, trypsin, and elastase. I believe these are all enteric proteases, and they all have very closely related structures, and obviously their active site geometry is very closely related. But for those of you that like convergence, the serine proteases are also a fairly good example of convergent discovery of the same active site chemistry. So sotolysin, which we've been talking about the last couple of slides in terms of enzyme kinetics, is structurally unrelated to chymotrypsin, and you can see that very clearly from looking at the amount of helical structure here, and reminding you that chymotrypsin looks like a pair of pseudo-symmetric barrels, whereas sotolysin is this sort of parallel beta sheet sandwiched between some alpha helices. In any case, overall structures very different, active sites identical. Let's also talk about papain. Again, an example perhaps of convergence to a similar chemistry. In this case, reminding you that the active site is not a serine but a cysteine side chain that is activated through this charged histidine. And so again, reminding you that it's this ion pair that's what drives the reaction forward. But in any case, you see that it's still a similar mechanism: activation of a nucleophile by this base. Right. So similar activities converged upon in nature. Blah 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 blah. The details vary, but the general chemistry is still quite similar. Getting back to the idea of binding and catalysis. Here's a structure of a chymotrypsin substrate, an ideal substrate for chymotrypsin, and we see that there are some binding determinants, right? There's this methionine side chain required here. There's a phenylalanine side chain required here. Here's our sissyl bond, right? Reminding you which bond gets cleaved. So you can see then that the organization of the binding sites for this substrate are very important for proper positioning, right? The selectivity of the substrate depends on the presence of these side chains in the proper positions relative to the bond that gets cleaved. let's look again at that specificity. This is something that we've worked on extensively in class. We see there's that phenylalanine, that binding determinant of phenylalanine, and we see that it lies in a very deep and very nonpolar pocket, which we've already discussed this, so I'll cruise right by it, reminding you that once we have a binding pocket, it's very easy to make some minor changes that drastically change the specificity of the particular enteric protease. We see again here chymotrypsin deep hydrophobic pocket. We see in trypsin a pocket that has at its base an acid residue, so we switch up the chemistry of the active site in that way. And then in elastase, what we see is that we've closed the pocket off with a couple of large hydrophobic residues. So simple changes to that binding pocket change the specificity of the enzyme for substrate, although we don't change the activity, right? We're still cleaving that same peptide bond. We'll leave it there, and we'll pick up with some other examples of enzyme mechanisms in the next video.